Hi all, in this lecture we will study Subgaussian random variables, which is a convenient and common class of random variables for which we can prove nice concentration inequalities. Then we'll study two classical concentration inequalities derived using the Chernoff method that we've seen earlier. One is called Hoeffding's inequality and the other is like an improvement on Hoeffding called the Bennett or the Bernstein inequality. So let's start out with defining Subgaussian random variables. So here a random variable x with 0 mean is said to be a Subgaussian random variable if there is some number v, a positive number v, such that its log moment generating function is upper bounded by lambda square v by 2, okay, for every value of lambda. Now just to refresh your memory, Cx of lambda is the log moment generating function of x at lambda, and if you recall, lambda square v by 2 is actually the log moment generating function of a Gaussian random variable. So e raised to lambda g, where g is distributed as normal with mean 0 and variance v. Okay, so this is the reason why uh, this random variable x is called Subgaussian. It's because its log moment generating function is upper bounded by the log moment generating function of a normal random variable with the appropriate variance, which is v in this case. So we use the notation g of v to basically denote all random variables which are Subgaussian with parameter, we'll also call it the variance parameter for reasons that will become clear later, v. Okay, so g of v is the class of all random variables which are Subgaussian with variance parameter v. And so we'll use the notation x belongs to script g of v, calligraphic g of v, if x is 0 mean and it is Subgaussian with this variance parameter v. So moving on, there are a couple of remarks about this definition of Subgaussianity. So it's easy to check that if you have random variables which are independent called xi, and each of them is Subgaussian with an appropriate variance parameter vi, then their sum is also Subgaussian, where the Subgaussianity parameter of the sum is simply the sum of the Subgaussianities of each random variable. The second point here is that if x is a Subgaussian random variable, then it's by definition 0 mean, and you have concentration inequalities that bound the probability mass of it exceeding a level t, a positive level t. So you immediately have, by the moment generating function bound and the Chernoff method, that probability that x exceeds t or minus x exceeds t is at most e raised to minus t square by 2v. So these are just applications of the Chernoff method. Okay, so by the Chernoff technique. Okay, because you have an upper bound on the log moment generating function, which is that of a Gaussian random variable. This will give you a lower bound on the dual of Cx lambda, which is Cx star of t. And that's precisely what comes into this exponent here. Okay, the third remark here is that it's easy to show that if x is Subgaussian with parameter v, then its variance is actually bounded by v. Okay, so this is the reason we call this parameter v as also as the variance parameter. Now the definition for Subgaussian random variables that we stated here is not the only one that allows you to specify a tail behavior for the distribution of such random variables. There are in fact several equivalent ways of being able to enforce a Subgaussian tail for random variables. So this is the following result. So if you have a random variable whose mean is 0, then the following statements are essentially equivalent for suitably chosen numbers v, b, c and d. Okay, so essentially up to constant scale factors, all these definitions give you the same property of a random variable x, which is essentially the fact that it has a Subgaussian tail. So the first property is our usual definition that we just made about x being V Subgaussian. The second property is the resultant Chernoff bound that you get for its tail, which essentially decays at rate e raised to minus constant times t square. The third equivalent characterization of a Subgaussian random variable says that if you take the expected value of e raised to cx square for some positive number c, for an appropriate positive number c, then it is bounded, it is finite. Okay, so such a random variable x enjoys finite expected values of its square, okay, constant time square. The fourth property is essentially controlling the rate of growth of the moments of the random variable. So if you take each even moment, which is expected value of x raised to 2q, then it's basically bounded by the rate of growth of the moments of a Gaussian random variable. So it turns out that if you do the computations for a standard Gaussian random variable, then the 2qth moment will essentially grow at this rate given by q factorial into, let's say, some constant 4 times d raised to q. Okay. We will not prove this theorem, we will just state this result without proof. Okay, because it will be a bit of a diversion from the flow of this lecture. So with this definition of Subgaussian random variables in hand, it's useful to study what types of random variables can be Subgaussian. It turns out that a large and commonly known classes of random variables that we have seen actually turn out to be Subgaussian. So the first step in our agenda to study Subgaussian random variables is what is called Hoeffding's inequality, which finally says that bounded random variables are actually Subgaussian. So in order to prove Hoeffding's inequality, which we will show later, we first need an auxiliary result called Hoeffding's lemma. So this is also lemma 3.3 in the concentration inequalities book, and it dates back to the work of Hoeffding in 1963. So the lemma is rather simple to state. So it says that if you have a bounded random variable, that means a random variable that takes values in an interval a comma b with probability 1, then it is actually Subgaussian with the following Subgaussianity parameter, the following variance parameter, which is b minus a the whole square by 4. Okay. So it helps you conclude that bounded random variables are Subgaussian provided you adjust the scale of the Subgaussianity appropriately. Okay. So so let's do the proof of this lemma due to Hoeffding. So there are several ways in which one can prove this lemma. We'll present one of them, which essentially uses the language of moment generating functions. So the first observation is to say that if x is a bounded random variable between a and b, then one can upper bound its variance as follows. So the variance of x is the same as the variance of x minus the midpoint of a and b. Okay. Okay, subtracting a constant does not change the variance, and the variance is upper bounded by the second moment because the variance is equal to the second moment minus the square of the first moment. So this is at most expected value of x minus a plus b by 2 the whole square. Okay, and since x is bounded between a and b and a plus b by 2 is the midpoint, the largest that x can deviate from the midpoint a plus b by 2 is again by a plus b by 2, and so this gives you a bound of b minus a the whole square by 4. Okay, by the way, this bound is tight. You can easily convince yourself that you can design an appropriate random variable x between a and b that meets this inequality with equality. The second observation is to say that so we have the notation psix of lambda is the log moment generating function of x at lambda. So let's make a couple of observations. The first is to observe that if you set lambda equal to 0, then you get log of 1, which is 0. And the same holds if you differentiate Cx of lambda with respect to lambda and set lambda equal to 0. Okay, so Cx of 0 is going to be equal to the derivative of Cx at 0, which is 0. Okay, so this is easy to check. Now let's move on to the second derivative of Cx. So let's compute the second derivative. Cx double dash of lambda at any lambda is by definition d by d lambda of Cx prime at lambda, which is just, so if you differentiate Cx once, you will basically get expected value of x e to the lambda x divided by e to the lambda x, expected value of e to the lambda x. And so we just differentiate this using basic rules of calculus. So on the numerator you will have expected value of x square e to the lambda x into expected value of e to the lambda x minus expected value of x e raised to lambda x the whole square, and in the denominator you will just have the original denominator the whole square, expected e to the lambda x the whole square. So one can rearrange this as follows. You can write this as distributing the numerator, you just have x square e to the lambda x divided by expected e to the lambda x minus the squared of expected x e to the lambda x divided by expected e to the lambda x. Okay, so this is just basic algebra and calculus. So now we'll do something non-trivial. We will define, so let x, let p be the distribution or probability measure of x, of the original random variable x. Okay, let's define a new probability distribution. So denote, so let's define a new probability distribution. Q on the same space as of values that x takes, as so we'll use the following formula. We'll say the ratio of q by p at every sample point is e raised to lambda x, x is the value of the random variable, divided by cx lambda to make it a valid probability distribution, that is to make it sum to 1. Okay. So the notation dq by dp, if you are not familiar with this, so you can just for concreteness imagine that x is a discrete random variable, and so this, if x is a discrete random variable, this just reduces to q of x by p of x. So when p is a discrete distribution, if p has a probability density function, then dq by dp is taken to mean the ratio of probability densities of q by p, and this can be extended even for general random variables. Okay. So in other words, an equivalent way of defining this new probability distribution is that for every event e in the original sigma algebra of x, the measure, the probability of the set E as measured by Q is defined to be the integral over this event E of e raised to lambda x with the original distribution p d omega, and you have to finally divide by cx of lambda, okay, to make it a valid probability measure. So this is basically how the distribution Q is defined. Okay, it's also called an exponentially tilted measure, because what you're doing is basically you're multiplying the original p by, you're hitting this original p by e raised to lambda x. So you're weighting up the probability distributions of values of x that are very high if lambda is positive, and down weighting the corresponding probabilities of the random variable when the values are low, when the values x of omega are low. So it's easy to see by a simple calculation that if you compute expected value under this new distribution Q of the same random variable x square, so this turns out to be integral. By definition, this is the integral over the entire sample space of x square q d omega instead of p d omega, and this is equal to, by definition, x square e raised to lambda x p d omega finally divided by cx, so divided by cx lambda. Okay. And so you'll easily see that cx double prime of lambda, which we were computing earlier here, which is this quantity here, in fact can just be written as eq. So the first term here simply becomes eq of x square minus eq of x the whole square. The second term is exactly eq of x the whole square. Okay. So this is eq of x the whole square, the second term here. And this is simply the variance of the same random variable x but evaluated under a different probability distribution Q. And since x hasn't changed, the random variable x hasn't really changed, so it is still bounded between a and b. And so by our variance result, its variance under any distribution, whether it is p or q or any other distribution, can be no more than b minus a the whole square by 4. Okay. So what we have shown is that the second derivative of cx, which is defined with respect to the original distribution p, is actually bounded. Okay. So you have a function cx as a function of lambda with some bounds on its curvature or second derivative. So the last step here is to use, so finally applying the Taylor series formula, so Taylor's theorem in the remainder form will give us the following. It gives that for any lambda we have cx of lambda is equal to, so let's expand this as a Taylor series about lambda equal to 0. So you have cx of 0 plus lambda times cx prime at 0 plus the second order term is going to be lambda square by 2 cx double prime at some number theta between 0 and lambda. Okay. So this is Taylor's theorem up to second order with the remainder term, and we know that this term is 0, this first derivative is also 0 at 0, and we know that the second derivative is bounded by 1/4. Okay. And so using this we finally get that this is upper bounded by lambda square by 2 into b minus a the whole square by 4, which is exactly what we wanted in the theorem. Lambda square by 8 b minus a the whole square. Okay, that concludes the proof of Hoeffding's lemma. So basically what we have shown is that for a random variable x bounded between the values a and b, its log moment generating function is always bounded by this quadratic function of lambda with a bound on the coefficient being b minus a the whole square by 8. Okay. So an additional note here that I'd like to add is that this lemma is actually tight. Okay. Meaning that you can actually find a non-trivial random variable x given any interval a and b, which for which the log moment generating function is exactly equal to lambda square by 8 b minus a the whole square. Okay. So once we have Hoeffding's lemma in hand, it gives you what is called Hoeffding's inequality, which is corollary 3.4 in the concentration inequalities book. Okay. So this is a concentration inequality that is obtained by by appropriately using Hoeffding's lemma. And it says that if you have independent random variables x1 through xn, which are each bounded in the respective interval ai bi, then the probability that their sum exceeds a level t. Okay. So I should also say that that all xi are zero mean. Okay. Then the probability that their sum exceeds t is at most e raised to minus 2t square by sum over all I of ai minus bi the whole square. Okay. So this gives you a way to control the deviations of bounded random of a sum of bounded random independent and bounded random variables. The proof is basically an application of Hoeffding's lemma. So it's just one line. So by Hoeffding's lemma, we have that the sum of these independent random variables must be Subgaussian with the variance parameter being equal to the sum of all their individual variance parameters, which by Hoeffding's lemma is ai minus bi the whole square by 4. Okay, so that's the proof once you have Hoeffding's lemma. So we'll now move on to proving what is called Bennett's inequality, which can be motivated by the observation that if you stare a little closely into Hoeffding's inequality, there's one issue or a weak point in Hoeffding's inequality. It's that it doesn't bring in the actual variance of the sum of all these xi's or the variance of, let's say, each of these random variables. So there's no dependence here. If you look at Hoeffding's inequality, there's really no dependence here on the actual variance of each xi. There's only a dependence in the worst case sense on the complete range of ai and bi. So for instance, if all these random variables xi were within very loose bounds a and b, which are very far apart, then you would have a fairly weak bound, because you know that with high probability they're actually confined to a much smaller range. Okay, effective range. So how do we bring in that measure of spread of each random variable or the spread of the sum? Okay, so this is one thing that Bennett's inequality will help to address. And so one version of Bennett's inequality is as follows. It's also lemma 3.5 in the book. So let's take independent and zero mean random variables x1 through xn, where each of them is bounded. It's the same setting as Hoeffding's inequality. So a bunch of independent zero mean bounded random variables, and let sigma square be their average variance. Okay. So this is not n here, I should say. It's this is not eta, it is n. So sigma square is basically their average variance. Then we can control the fluctuation of the sum of these independent random variables by a quantity that depends on the variance, the average variance here. Okay, so the sigma square appears here as well as here. Okay, the function h here is something that we have seen earlier, which you should probably recall as related to the Chernoff method or the tail probability bound for a Poisson random variable. Okay, so this appears, and we will make the connection to a Poisson random variable in the proof. Okay, so the upshot of this inequality, Bennett's inequality, is that it gives you actually a way to bring in the actual variance of the sum of these random variables x1 through xn, and one can stand to benefit if the actual random variables enjoy a much smaller variance than their worst case bounds ai and bi. So let's go on to prove this inequality. So the first step of the proof is to write out is to bound the moment generating function of each random variable xi. So let's begin by writing the expected value of the moment generating function of any xi. Okay, so this is by definition, if you just expand it out as an infinite power series, this is k equal to 0 to infinity, lambda to the k, expected xi to the k by k factorial. Okay. So since the first moment is 0 by assumption, let's take out the first two terms. The first two terms are 1 plus 0, and let's write this sum from k equal to 2 onwards. Okay, the k equal to 1 term is missing because the expected value of xi is assumed to be 0. So this is lambda to the k expected xi to the k by k factorial. And we'll now perform the following bounding operation on the summation on the right. So this is 1 plus, this is at most 1 plus the sum over k equal to 2 to infinity. So we'll have lambda k by k factorial. So what we'll do is, from expected value of xi raised to k, since k is at least 2, we can take out xi square, and then we can keep the remaining xi raised to k minus 2. So we have expected value of xi square and the absolute value of xi raised to k minus 2. Okay. So by putting the absolute value in, we can make an upper bound. And let's now invoke the bound that the absolute value of xi is at most c. Okay. So that whatever is remaining is the expected value of xi square, which is just its variance. So this is at most 1 plus the sum lambda k by k factorial. So the absolute value of xi is bounded by c, and then what remains is just the variance of xi. Okay, let's denote this by sigma I square. This is the variance of xi. So finally what we have is the expression 1 plus sigma I square by c square sum over k equal to 2 to infinity lambda c raised to k by k factorial. So I've taken out the c to the minus 2 outside, and this in turn is just 1 plus sigma I square by c square. Okay, so this is just the power series expansion of e raised to lambda c minus the first two terms, minus 1 minus lambda c, and we'll use 1 plus x is less than equal to e raised to x now to make an upper bound here. Sigma I square by c square e raised to lambda c minus 1 minus lambda c. Okay, so this is because 1 plus alpha is at most e raised to alpha for any value alpha. Okay, so finally we have, so therefore we'll be able to extend this to the sum of n independent random variables to show that c of summation xi I equal to 1 to n at lambda is just equal to the sum over all the i's. Well, I think it should be an upper bound. Okay, from I equal to 1 to n sigma I square divided by c square and e raised to lambda c minus 1 minus lambda c. This is just by summing this inequality above. Okay, for all I equal to 1 to n. Now this kind of log moment generating function bound is something that we have actually seen before, and just to refresh our memory, let's recall the following fact, that if x is a Poisson distributed random variable with some parameter v, then its log moment generating function, when you center it by v, by its mean v, is v into e raised to lambda minus 1 minus lambda, and its dual function cx star, its Kramer transform of the centered Poisson random variable, is v times h of t by v. Okay, where h of x is basically the same function h, 1 plus x log 1 plus x minus x. Okay, so this is a fact about the tail of a Poisson random variable, or the moments of a Poisson random variable, and we can now do some pattern matching here. So this expression here can somehow be thought as this here. Okay, Okay, so we have now that psi of the sum of I xi at lambda is at most n sigma square. Okay, so this summation of all I sigma I square is just n sigma square by definition, n sigma square by c square into e raised to lambda c minus 1 minus lambda c. Okay, so let's compare this moment generating function for a centered Poisson with this expression which we have obtained for our sum of xi's. Okay, so it follows that one can set v as n sigma square by c square, and by doing this, by making this connection, you can find the dual function of this right hand side expression here to get the bound c star of summation I equal to 1 to n xi at t is lower bounded, because the primal function c is upper bounded. It will imply essentially a lower bound for the dual function by the definition of c star. So you get finally, after some algebra, n sigma square by c square h of t c square by c n sigma square. Okay, and this is the same as n sigma square by c square h of tc by n sigma square. Okay, so this is this should be what we want. So that's n sigma square by c square h of tc by n sigma square. So that's exactly the expression that we wanted, and this implies the tail bound that we seek. Okay, so that's the proof. So the proof essentially involved uh, not succumbing to using the standard Subgaussian bound from Hoeffding's lemma for these random variables, but actually keeping a dependence on their variances and directly relating the moment generating function of each random variable to its variance, and finally connecting it to the uh, moment generating function of a Poisson random variable. So that's Bennett's inequality. Now Bennett's inequality is phrased in terms of this h function, which has essentially an x log x type dependence, and often Bennett's inequality is simplified to get a more transparent insight into the tails of random variables depending on their variances. So here's one such consequence of Bennett's inequality called Bernstein's inequality. It's given in corollary 3.6 of the book. So Bernstein's inequality basically says that in the same setting, that is, if all these xi's are zero mean and bounded in absolute value by c, then the probability that their sum exceeds a level t is at most e to the minus t square. So this is basically in the exponent is a ratio of polynomials. There's a quadratic polynomial on t on top, and there's a linear polynomial depending on t in the bottom. Okay, so so this form is what you get as a consequence of Bennett's inequality. Okay, so the proof is by using Bernstein plus the elementary bound. So by using Bennett plus the bound. So the h function can be bounded below uniformly. So x cube by 2 plus 2/3 x. Sorry, this is x square. Yeah. Okay. So this is a universal bound on the h function, and using that in Bennett just gives you Bernstein's inequality. So let's do a quick example here to understand what Bernstein gives over and above what Hoeffding could have given you. So we'll take the simple example where xi's are all Bernoulli random variables. They're IID Bernoulli random variables with parameter p, and Sn is their sum. So in other words, Sn is a binomially distributed random variable with mean NP. So Hoeffding would give you the following. So just applying Hoeffding on these, would give you that the probability that Sn minus its mean, which is Np, exceeds a positive number t is at most e raised to minus 2t square by n. So a and b are set to 1 here because that's the range of every Bernoulli random variable. So equivalently, the delta form of Hoeffding's inequality says that with probability at most delta, this event occurs, Sn minus Np exceeds, so in fact you can put greater than equal to square root, so it's basically square root n into log 1 by delta, okay, at most delta. Now contrast this with Bernstein, okay, which would give you the following inequality: probability that Sn minus Np exceeding t is at most e raised to minus t square by 2 times n times the variance of each Bernoulli, which is in this case p into 1 minus p, plus 2t by 3. Okay, c is set to 1 here, which is the range of each random variable. Okay, it's a little more transparent if we try to find the delta form of Bernstein's inequality in a somewhat more tedious manner. So let's try to find the delta form. So to find the delta form, we need to equate the right hand side of this inequality to delta and solve for t. So that means that t square equal to 2np 1 minus p plus 2/3 t log 1 by delta. Okay. Okay, that's the only way that the right hand side will become e raised to minus log 1 by delta, which is delta. And it turns out, so this is a quadratic equation in t, and it turns out that if you actually solve it in closed form, you will get t equal to 1/3 log 1 by delta plus 1/3 square root log 1 by delta whole square plus some constant 72 np 1 minus p log 1 by delta. Okay, all under the square root. And you can just upper bound this if you like by log 1 by delta plus 4 times square root np 1 minus p log 1 by delta. Okay, for delta upper bounded by some number delta naught, for instance. Okay, so for small enough delta, this certainly holds. And so finally, you will get that the probability that Sn minus Np exceeds this number, which is log 1 by delta plus 4 square root Np 1 minus p log 1 by delta. This event occurs with small probability. Okay, so just to remind you what Hoeffding would have given for the same delta target probability of error. So let's compare with Hoeffding. So what would the typical deviation from Hoeffding be? It would be basically square root n by 2 log 1 by delta. Okay, so the way to compare this, so one way to compare this is let us say that delta is set to some small number, delta is fixed at a constant, so log 1 by delta is a constant, and n is a large number, n is a fairly large number. So here this quantity goes basically as square root n, whereas this quantity actually goes as square root n into p1 minus p. Okay, so this is very useful if p into 1 minus p is a fairly small number. So if each of the variables, the Bernoulli variables xi, have very small variance, then one could actually gain by reducing the deviation of from Hoeffding, which is order square root n, to something which is of order square root of n times the variance of each Bernoulli. Okay, so so this implies that we gain when p into 1 minus p is small. Okay, so for example, here is just a case, just as an example, there could be n Bernoulli random variables. So xi, iid, Bernoulli p, I equal to 1 to n, where each, so let's say the variance of xi is for instance 1 over n itself. Okay, so in that case, uh, so one way in which the variance could be 1 over n is basically if p is itself of order 1 over n. Okay, so if that is the case, then you basically get a constant deviation, constant scale deviation here, because you have inside the square root n multiplied by 1 by n, which is much better than what Hoeffding could give you. Okay, so basically you gain when the variance of the xi is fairly small. So that's where Bernstein is often used to get you the additional gain from exploiting random variables that are effectively quite small as measured by their variance. That concludes this lecture. Thank you.